Greetings and welcome to a new video. In this video we will discuss the voltage regulators. This is a configuration where we have a series voltage regulator. Of course we will see a design example and work out the calculations step by step and verify these in SPICE simulations. Okay, before we jump to our example and a design, let's first discuss the voltage regulation. We have the line regulation and the load regulation, so we will discuss these briefly. If you have a specific input voltage that is changing because of some effects in the circuit or some other parameters in your circuit, the voltage regulator in between must maintain the output voltage as you want it in a nearly constant value. For example, if you have your input voltage at 10 volts and you require the output, let's say 6 volts, but the input is changing, going up or going down, your output voltage will then stay at that exactly the value what you want, or really close to that value. That is what we call the line regulation. So in summary, we can say if we have the input voltage which is changing, a regulator is required to keep the output voltage at some constant or stable value. And there is a formula for that. In order to make that more precise, we can say the line regulation is given by this expression, which is a percentage by volt. So you can see actually the change in the output voltage, so the percentage change in the output voltage divided by the change in the input voltage times the 100% here is then given by this unit. This is a nice expression to look at your line regulation. And when you talk about the load regulation, you actually consider the load voltage and the load current, and of course your load resistor will define that. So if you have an input voltage which is in this case some value, the regulator again here is to make that load current, if that is changing, not affecting the load voltage. So if the load current is changing because of the change in your load resistor, because that's going up or going down, so you require more current, the load voltage must then stay again constant or stable. So we need to keep it again stable. There are of course two conditions, two extreme cases. We can have absolutely no load, so this is the open circuit, so that means no load, but you can also have full load, that means you have actually a short circuit there. So those two conditions we require to define now in this case the formula for the load regulation. That is given by this expression. So load regulation is the no load condition for our output voltage minus the full load condition divided by the full load condition of your output voltage times again 100%, just to convert this in percentages. Okay, let's go to our design example. We have here a series voltage regulator given. This is the circuit we will use for our design. In this case we would like to design a nearly constant output voltage of 7.5 volts, and we also discuss some effects of the input voltage and changing in the resistor R1, and also what we have if you change your load resistor. But before we jump to the actual design and the calculations, let's briefly discuss what this circuit is doing. We have here several components. We have the error detector. We have the Zener diode, which will set our reference voltage here. We have here the control element, which is there to control the current here. And we have here the sample circuit, which is in effect a voltage divider. We also have our load here. So in this case, we have the operation of the series regulator as follows. So if your input voltage, then the output voltage attempts then also to decrease, because if this is decreasing, then it will have an effect on the output. Now the feedback voltage, what we have here, the VF, will then also decrease, because if the output voltage is decreasing, then the voltage divider rule will create, then this is also decreasing. Now, as a result, the op-amp's output voltage, VB, which is then the base voltage of this Q1, will be then increasing. Why? Because if this is going down, and this is then set at some specific reference value, then the positive voltage, or the voltage at the non-inverting input, is larger than the voltage at the inverting input. So the error amplifier detects a positive change here, or positive error, so that will make then the VB larger. Now if the VB is then increasing, then it will then surge more current here, so it will then compensate the decrease of this V out. So by increasing actually the emitter current, which is then actually this current for the Q1. Now when then this is stabilized, then everything is then again back to the original situation. But if your V in is increasing, that can also happen, then V out is also attempting to increase. But if this is also increasing, which is of course not what we want to stay stable at some value, then this VF, which is our feedback voltage, is also increasing. Now if this is increasing, then this will be then less positive, so the Vref minus the VF will be then less positive. So the error here will be then also smaller. Then the VB will be going down, so you will also surge less current. That's why this is a control element, the Q1, and then you also control again your V out such that again everything is settled to value you want. That is in briefly the operation of this circuit. Let's see how we can work out the calculation for our design to create here now 7.5 volts, because we need to calculate some resistors and also select the diodes and the transistor here and also our operation amplifier. So we need to do some selection, also some calculations here. So let's see our calculations step by step. In this case we will select a reference voltage. This is really an arbitrary value of 3 volts here. So our reference here is 3 volts. That means for our xenon diode we need to select here a xenon diode which has a breakdown voltage of 3 volts. That is the first selection we have made. Now initially we will select an input voltage which is slightly larger than the output voltage. In this case I will take 8 volts here. So that will be then a little bit larger than 7.5 volts. Why? Because if I take this, for example, 6 volt in order to continue with my design, this transistor will never be active. So actually I will then never have a current conduction here. So I will then have not my 7.5 volts at all. So we need to just stay a little bit above that value you have here. And then we can see what the effect is if this is really going down. Now depending on the required zener current, because the zener diode is not just a breakdown voltage, is also affected by the zener current here, because this current here, IZ, and this voltage here, VZ, that together makes that zener diode operate. So if we select the zener diode, which has a breakdown voltage or zener voltage of 3 volts, at that specific zener current, which is in this case, let's say 5 milliamps, really arbitrarily chosen, then we have the following expression we can make for this R1. Because this loop is then using Kirchhoff's voltage law, we can say R1 is then equal to V in minus the Vref or VZ, which is the exact same, divided by the current flowing in this branch. Now there's no current flowing in the operational amplifier input, assuming an ideal op-amp, and the input impedance is infinite. So we can say this is now the expression we need to use, and now we do 8 minus 3 over the 5 milliamps, 0.005, which is exactly 1 kilo ohm. So we know that our resistor R1 must be 1 kilo ohm. What happens if I choose this smaller, let's say 900 or 800, then I will surge here more current. That will create a little bit larger VZ, so the zener voltage will also a little bit go up. That's the effect of this decrease of the R1. If you make the R1 larger, then you create less zener current, so it will also lower the zener voltage. That is the effect of this R1. Now, to have an output voltage of 7.5 volts, we also need to know what the values of this R3 and R2 is. So we need to calculate also these values. So neglecting the base emitter voltage of this base emitter voltage drop of this Q1, this resistor, this transistor, which is approximately 0.7 volts, but let's just ignore it for the moment. Then we can write actually expression which is familiar from this amplifier circuits we have, non-inverting amplifier. So we can say this voltage will be amplified by 1 plus the R3 over R2. And that is the expression we can use, this approximate expression. And then we can say what is now the R3 over R2 value. Now that is then just rewrite this formula and then do minus 1 here left and right hand side, and you have now here, by selecting your 7.5 at the output and the reference voltage here of 3 volts, minus 1, you get now here exactly 1.5. So we need to have a ratio of R3 over R2 of 1.5. Now this can be done pretty easily by selecting, for example, R2 has 10 kilo ohms, then we need R3 of 15 kilo ohms. Of course, many other options are available. Okay, now we have made our calculations by selecting some values, of course, and some components. In this case, we have an input voltage of 8 volts. That's the initial what we will do. Zener diode will have a breakdown or a Zener voltage of 3 volts at that Zener current of 5 milliamps. And now these are the 3 resistors we have chosen or calculated. Now we will also choose here dual power supply for our error amplifier, and our operational amplifier here will be TL081. That is again a choice here. The transistor Q1 will be BC546, which is an NPN BJT bipolar junction transistor, and the Zener diode here is 3 volts at 5 milliamps operation, which is then this type. So I have just searched for this specifically and then found that this is indeed having a 5 milliamps Zener current and 3 volt Zener voltage. And the resistors we have calculated were 1 kilo, 10 kilo ohm and 15 kilo ohm here. The load resistor is not defined yet, so we need to determine that. That will be then discussed later when we look at the effect of this load resistor RL. Okay, let's now look at our simulation results. The initial design with no load, which is actually, this is an open circuit, which is then this circuit here. What you see here in the SPI simulator is which is our input voltage 8 volts, R1 is 1 kilo ohm. You see here our Zener diode exactly as we have selected here. The operation amplifier TL081, the Q1, which is our transistor, and we have here also the resistors R1, R2 and R3. Now you see also here the 20 and the minus 20 volts we use for powering up this operational amplifier. What do we see? Now exactly as we have expected, the 3 volts here as the V reference, 7.5 volts at the output, so that's also exactly as we wanted. We also see at the VB, which is our base voltage, which is 8.13 volts. So this is actually a little bit, let's say approximately 0.6 or 0.61 volts above actually this one. So you see here a voltage drop which we have ignored, but it is there. So there's actually some value here, but still this is getting to that 7.5 volts because of this negative feedback operation. So we have achieved our goal in our initial design. Now let's now look at the other effects, because we have some things to check here, because we like to check the effect of on the output voltage when we change the input voltage. So that input voltage will now also be swept, so we will change the value. Again, we use no load, so this is an open circuit. Now these are now the plots we have. You see 3 plots. The top one is for the base voltage, which is actually the voltage at this node. The middle one is the output voltage, the blue one, and this red one is our reference voltage. Now what we see here is the following. The output voltage, let's start with that one, is, and this is the input voltage by the way, so we sweep from 1 volt up to 14 volts. Now you see the blue line is increasing linearly when you increase your input voltage up to, let's say, approximately 7 volts, and then actually 7.5 volts, maybe 7.4. So this is doing linear operation. That's actually what we have discussed briefly before, because if you make your input voltage less than your anticipated output voltage, then you will have a linear relationship, so you will create increasing output voltage, so there will be no constant or stable output voltage. Now when this is happening, when you have your your input voltage, I mean 7.5 volts, you will create at the output that also very closely. So you see actually here 7.5 volts is now created. If you increase your input voltage further, 9, 10, 11, etc., this is staying fairly constant to that 7.5 volts. This is also happening with the base voltage, because the base voltage is a little bit larger than the output voltage because of this voltage drop across the base emitter junction of this Q1 transistor. So you see actually the same linear relationship, but is of course shifted up by approximately 1 volts, and then the base voltage is also getting constant when we reach our value here for the input, which makes the output again constant. What we also see for the reference is that it is also not always 3 volts. It is really increasing rapidly, and when you have sufficient voltage at the input, it is also getting closer and closer and closer to the 3 volts. At the 8 volts we have at the input, it is indeed 3 volts. But if you go down to 7 or up to 9, etc., it is still in the vicinity of that 3 volts. So the reference is pretty close to what we want to have, which is 3 volts. Okay, let's now look at the effect of the resistor R1. Because if the R1 is changing, we already discussed that briefly, the current what we search here, which is also going through the Zener diode, will also change. And this is now the plot which we have here. We see actually here again the three plots: the base current, the base voltage, the output voltage, and the reference voltage. Now the reference voltage, let me start with that one, is starting a little bit higher. Why? Because if you start here from 200 ohms up to 2000, so 2 kilo ohms for our R1, for 1 kilo ohm, it is indeed VRF at 3 volt. If you go down, you search more current because this is now getting less resistive. So you search more current, but still this is not a really high increase because it is only going from 3 volts to 3.18 volts. So still not that much in percentage, not a very high difference. But if you increase your resistance, so the R1 is going up, you will see that you're also getting less Zener current, also then the reference voltage also go down. But if you look at it, if you increase the R1 from 200 all the way to 2000, so make it 10 times larger, your reference voltage goes down from 3.18 to, let's say, 2.9, which is not that big difference compared to this huge difference in the R1. So this is pretty stable if you look at this plot. Now for the output, you see that it is indeed different because it is going all the way maybe to 7.95, so let's say 8 volts there. But it is going down, 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 and then it reaches 7.5 at this 1 kilo ohm. It's also again decreasing to, let's say, 7.3 volts. So it is actually affected by this R1. So this R1 need to be selected carefully in order to have this 7.5 volts or the value you want at the output. So this is affecting the output in this case significantly. Now we can also see what the base voltage is doing. Again, this base voltage is some voltage drop here above this output voltage. So you can see here this voltage is base emitter voltage drop plus the V out here. So if this is, let's say, 0.7 in the standard form, then you will have this voltage plus 0.7 will be here. Of course, this is not always the case for each current condition, but this is approximately the case for this pink line. Now let's now look at the situation, which is one of the important things, the effect of the change in the load resistor. Now the load resistor is there, so we connect the load resistor here. And now we will see what the effect is if we change the load resistor by keeping the other values the same. So the input voltage is 8 volts. The rest of the parameters are exactly as we have calculated. So the initial values of R1, R2, and R3, and also the components we have chosen are there. What we see? Now we have again the base voltage, output voltage, and the reference voltage. The reference voltage is here very close to 3 volt. It looks like it's increasing. It's actually a very tiny increase here, so it looks like increase, but it is actually almost 3. And we see here that our load resistor, RL, is going from 10 ohms up to 140. So we see actually a huge change, but in the reference voltage we see almost no change. Why? Because this change here at the output is not affecting what is going on here, because this current is always the same. No matter what you do here, if you make it short or open, it doesn't matter. You will get the current here for the Zener diode and also the voltage for the Zener diode. So this is not a surprise, but this is interesting to see, V out. If you make a very low load resistor, you will surge more current. So you actually require more current, and that is not what the operation amplifier can deliver. And that's why this output voltage is dropping drastically here. So it is actually starting at almost 5.7 volts. But when the load resistor is increasing to 20, 30, etc., and at some point, which is actually shown here as 61.45 ohms, it is reaching that 7.5 volts. And then the pink line, which is our base voltage, is then reaching that 8.94 volts. This, of course, not 0.7 volts above the 7.5 volts. It's much larger, so almost 1.5 volts. So this is almost 9 volts there. So what happens then? Now when you increase this load resistor further, you can see that also here 70, 60, 60, 70, 80, etc. Then this pink line is going down much faster and then also stabilizing a little bit. But you see here the blue line, which is our output voltage, is fairly constant and almost actually 7.5 volts, even though we change our load resistor here. So now that you see the load regulation, this is now 70, 80, 90, 100, etc. Doesn't matter. Your output voltage is this 7.5 volts. Of course, a very important note here, it is not for all load resistors, because if you go down from 61 ohm, let's say, go down to 50, 40, etc., you will see a drastic decrease in your output voltage because you draw more current from your operation amplifier, and that is not what the operation amplifier can supply. So we need to maybe go then for a different error detector or a different operation amplifier and also a different transistor. That's actually the message from this analysis. Okay, now we see also here the plot again for the extreme case, where you see here the 61.45 ohms. It's actually what you see here. Now again, the reference is still 3 volts, so that's not changing. Again, the input is the same as before, so 8 volts. And now you see here indeed that this is almost 7.5, and you see also here this 8.94 volts. That's also what we have discussed here in this plots. Alright, it was our example considering the series voltage regulator. We have discussed how we can make a design for the nearly output voltage, which is 7.5 volts. We also discussed the effect of on the output voltage when we change the input voltage, the resistor R1, and also the load resistor here. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.